So, welcome everyone. My name is Gabriele. I'm a software engineer. By day, I'm an engineer at Buildo, a company that I co-founded. It's based here in Milan, actually very close to here. We do web applications using several technologies that I personally like, including TypeScript, React, and a lot of Scala. So I'm actually more a Scala developer than a JavaScript developer, but as you will see today, the topic of today is very general across languages. By night, I do a few things in the world of open source and communities. I run the Milano Scala group, which is the user group of Scala in Milan, which is confusing to most people because, you know, Scala. And the Scala Italy conference, which is an annual conference that we organize in a different city every year. And then I contribute with talks and talking stupid shit in the communities at Milano.js and Italia.js in general. So, why this talk? So, essentially, this talk is an excuse for me to do some live coding of a lot of plugins, like ESLint. We will see Babel. We will see a few other things. But what I noticed working with DevTools, which is kind of the topic of today, there is this fil rouge. There is this connection between these topics of doing things that improve developer workflows across languages. So this is for JavaScript, this is for Scala, this is for any other language you may encounter. And the foundation of this thing is AST syntax trees, as we will see today. So the agenda of the talk today is talking about AST syntax trees in general, what they are, brief introduction. I'm sure most of you already know some of it. We will see how these AST syntax trees are used in very common workflows in the developer life of everyday programmers. And we will see a real-world example of how can we use this knowledge to improve things that we're doing by hand. So let's start from the answer. Of course, it's 42, like in every talk ever. And so this is a JavaScript statement. It's a declaration of a const. And so if you want to do something useful with it, like anything useful other than reading it, and probably even reading it to some extent, you want to transform this into something more easy to manipulate, like a data structure. That could be a tree, that could be any other data structure. The most common one is trees, and we will get there. So the first thing you can do is to divide this statement into tokens. So tokens are kind of the alphabet of any language. In programming languages, tokens are this undivisible thing. You cannot split it further than that. And some tokens are keywords like const, some tokens have this special meaning, and some other tokens are just names or literal, so you can just parse these into tokens. But of course, you know all that. So like in any also natural language, you cannot just take these words and arrange them together in any way. Like you don't make sense if you do that. You need to have some rules that tell you how is legal to arrange these tokens together. So this thing is usually called a grammar in natural languages, and it turns out that in programming languages is a grammar too. So a grammar is the set of rules that arrange these tokens together. So a grammar describes what a syntactic valid program is. So it doesn't have to make sense in terms of what it does, but it's a valid program. So as you will see here, the variable declaration statement that we were looking at has several parts. Has to have a keyword on the left, which can be const, var, or let, but use const ever. So then you have a variable declarator. Why a variable declarator? Because you can have many of those. So you know, in JavaScript, you can just put a comma there and define many other variable declarators without repeating the keyword. So you can have that. And then a variable declarator needs to have a thing on the left, an equal, and a thing on the right. So the thing on the left is usually a name, an identifier, and the thing on the right can be any arbitrary expression. So we break it down to the tokens, and as you may notice, this forms a tree because it branches out until you get to the tokens. So we're starting to make sense of the acronym. So abstract syntax tree, we've seen is a tree, okay? And it describes a syntax because it abides to the rule of a grammar. So it's a syntax tree. Why is it called abstract, okay? So it is abstract because there's a lot of things that we programmers love to argue about, like semicolons, spaces, tabs, these kind of things. They don't matter. Sorry to tell you about that. We can talk about that all day, but they don't matter once you transform that into an abstract syntax tree. Because all the information that you need is actually that thing is a const, the name is answer, and the value is 42. Everything else is meaningless once you move forward and you want to execute the code or do anything useful with it. So here in the abstract syntax tree representation that it's on your right, you can see that those information are preserved, but information about the spaces, the new lines, of those boring things are just thrown away. And that's why it's abstract, because you lose information and you abstract away those informations, and it's not concrete in the sense that you cannot just take this and go back to the original code. It could be any code that compiles down to this one. Okay? So we're losing information when we're transforming code into abstract syntax trees, which is crucial in a few applications that we will see very soon. So, JavaScript. So everything I said so far is very generic. You can take this in any language that I know. You can parse any statement of any language into tokens and into abstract syntax trees at some point, which is reasonable. And every parser does that. But in JavaScript, we have several, of course, competing standards. Probably because writing parsers is easier than it should. But also because, for historical reasons, as you may see, the names of those nodes and the fact that they are arranged in that way, that the structure is arbitrary. I mean, you can define your own if you want. The fact that you have a variable declarator that is inside a variable declaration, which can be of any kind, like const, let, or var, is arbitrary. You could have 3 different nodes for doing the same thing, like one for const, one for let, and one for var with slightly different rules. So that's a choice that someone has to make. And it turns out that these choices have been made a few times with different results. So if you go home after this talk and you want to try things out, you want to like manipulate some abstract syntax trees, try to hack on some JavaScript and try to see what you can do with it, and you Google for it, you'll find probably a subset of these names all around. So I just want to give you a hint of what they are and why they exist so that we can move forward and have a common language to talk together. So in the first column, we see parsers. And parsers are programs that turn code into trees. That's it. And ASTs are different specifications of existing ASTs. So the most common one that you will see very often in the slide is ES3. And ES3 is essentially the specification of the original, is a modification of the Mozilla implementation of a abstract syntax tree, which when they had to make the API public, the parser API public a few years back, I think like 10 years back, they decided to document it, and that evolved into being ES3. So ES3 today is used by many parsers, and it's a specification which is very well used. But it's not the only one. So if you know, like Babylon is the parser behind Babel. So Babel is a toolchain, has many different parts, the plugin system, the pretty printer, everything. It has a parser. And Babylon parser used to use ES3, but why not? They decided to fork it and to add some custom nodes to it. So Babylon is not ES3 anymore, is ES3 plus some stuff, plus some modifications. And of course, then you have other parsers like Flow that need to handle stuff like types. So types are not in the JavaScript specification. There will be eventually, probably, hopefully, but they're not today. So Flow needs to add custom nodes. It needs to add nodes for type annotations, for interfaces, for any useful thing that you have in Flow. But thank God, Flow decided to be retrocompatible with ES3 in a way, in the sense that it's an extension of ES3. So it extends ES3 to provide extra nodes and extra attributes on the nodes. And then you have TypeScript. And TypeScript is a completely different story. It's a completely different parser and a completely different AST, because TypeScript started something like 5 years ago, and ES3 was not that standardized at that point. So they just started from scratch, and of course, the result is very different. So TypeScript is completely different than the other ones. The other ones are very similar between each other. This one is not. Why so many parsers, by the way? So the oldest one of this bunch, I think, is Esprima. So Esprima was very popular a few years ago. Then it kind of stayed behind in terms of features with ES6. Has not caught up, as you can see. It supports the latest specification. But that was enough to fork it. So I think ES3 came along, forking Esprima to provide a similar API, but with supporting new features. Acorn, which is the first one, did the same thing. Now Esprit is based on Acorn. So there is this entanglement of parsers. The most forgiving of everyone is Babylon, because Babylon supports every feature of JavaScript that came out yesterday. Okay, so in terms of features, Babylon supports everything. So if you need to try out the new fancy syntax that some guy invented and it's in stage 0, you can try Babylon. For the other ones, they're more conservative. And especially Acorn only supports stuff that is in stage 4. So in the process of being approved to be a feature of the language, stage 4 is the one that is considered mature, and it will be in the next specification in the of the language. Esprit does the same thing, and Esprima, for instance, just supports the latest specification and nothing more. So these are all the things that are extremely boring, but that you have to know, because otherwise you may be hitting on a parser error, and you don't know if it's you, if it's the parser. So my advice would be, if you need to hack on something very quick, just use Babylon. It supports everything, but it has a slightly different AST than the other ones. To see all these things in action, you can go to this website, which we will use in the demos in a few minutes, and it's called astexplorer.net, and you can go there and type stuff in, and you can see the result on the right. So you can switch parsers and see how the different parsers produce a different result. Okay, and that's very useful because we will see how you can also use it to hack on different languages. So for instance, I personally added support for Scala. Who would have thought? Scala in the browser, you can parse a Scala program, have the Scala syntax tree. You can do the same thing with CSS. If you're doing some post-CSS work, you can do SQL. You can do a bunch of languages that I wouldn't think it would be possible. But any language that is parsed that essentially has a syntax tree. So that's a very good resource to play around. So let's talk about workflows. Okay, so in the developer life, when you're writing code, there's stuff that is happening, either in consequence or because you're causing it. And the most basic one is executing code. You write some JavaScript, you have some source, and somebody executes your JavaScript. And that's what browsers do. That's what Node.js does. So the first step in any of those engines is to parse your code into an abstract syntax tree, and then magic happens. Okay, so that's a very basic workflow. But of course, it needs to happen. So abstract syntax trees need to be there, and that's why every browser implements a version of this. The Babel workflow, which you may be used to. So for those of you who live on another planet and don't know what Babel is a tool for transforming modern versions of JavaScript into older versions of JavaScript, possibly doing some custom modifications in between, and we will see. And the purpose is to support all the browsers. So maybe you have a browser that supports only a certain subset of features, and you want to support that. You can take Babel and transform the trees into trees that are understandable by that browser, and then just print it back. And we will see how in a second. The interesting thing here that the transformation happens at a tree level. So you need to go into the tree world, which is this magical world where things make sense because have semicolon and stuff, and then you transform that and you print it back. So there is this parsing, transforming, and printing. And this is the full toolchain that Babel supports. So let's do a demo here. If our gods assist. Okay, perfect. So this is AST Explorer, the website that I mentioned. So you can go here and choose between these languages, and essentially JavaScript is the default choice. So you go here. So suppose now you want to write a Babel plugin. So a Babel plugin allows you to do your custom transformations to the trees, and is essentially the same mechanism that they use for like stock transformations, like transforming from ES 2017 to ES 2015, for instance. They have their own plugins, but they're written in the same way. So if you can go here and do transform and choose an API, I choose Babel v6 because it's the latest one that I know that works. And you can see here in the bottom left, you have the code of the transformation, and on the right, you have the output. Okay, I try to enlarge it as much as possible, but I need also to see what I'm doing. So let's take this off, and suppose that we have our code as before. And suppose that now, for some reason, you just want to take every literal number. I was about to say integers, but yeah, no. Number, and transform it by adding +1 to it. You can do it with Babel for some reason. And you can just go here, and you have this. You can take this off, which is useless. You have this visitor. And this is very common across APIs that work with trees. You have this visitor, which is essentially an object that partially matches part of the tree and allows you to hook into it and transform the tree as the parser is traversing the tree. So what you can do is to essentially query for this. You can go here and see that 42 is a numeric literal. This is the type of the node, and that's the power of this tool, because you can dynamically inspect what is the source. So const here is a variable declaration, and 42 is a numeric literal. So you can just go here and do something like this. Okay, I won't delve into the API's details that much. Just trust me, this works. So you have this node. what you want to do. So you want to take this node value, which is here, okay, and do node.value plus 1. Easy, okay? So now you just transform the tree, and then it gets printed back. So you're not touching the source code directly. You're not doing text manipulation. You're doing the structure manipulation, and you're just taking the node and changing it, and then Babel prints it back, and it looks like that. And you usually don't see Babel's output, so you can do fancy stuff and replace it with custom contrast that will essentially do anything that is useful for transforming code in older versions. And you can imagine you can do more complicated stuff, but timing is running tight. So let's go back to the slides. So this is an example of a custom transformation. And another possible transformation which looks really similar is CODEMODs. Who doesn't know what CODEMODs are? Okay, good. So CODEMODs is a name that is not very standard, I would say. It's very specific to the JavaScript community, but the idea is very standard. It's taking your code and refactoring into other code automatically. That's it, essentially. So if you're working, for instance, with React JS, they tend to release these CODEMODs when they really introduce breaking changes in the API, which is very nice. So you want to upgrade to a newer version of React, you can run this thing on your code bases, and it essentially changes your code to use the new API and to remove deprecated uses of the API. So it's essentially an automatic refactoring as a source code that you can essentially take that, run it, and you get your source code modified. Isn't that the same thing, though? I mean, if you take a look at this, it's very similar. Like, you're taking source code, you're transforming the tree, and you're printing it back. The process may be the same, but there is a huge focus here on the arrow here on the right. Because this code, you're going to take, read, and commit back to your repo. Okay, so this code is code that you will edit again, and needs to be written by humans and readable by humans. Okay? So the idea of a CODEMOD is to be conservative in what it does, which is not the idea of Babel. Babel can do anything that you like. If you've seen Babel output, is not exactly readable, and you may read it, but you're not going to commit that back into the source, right? You're just going to use it to run it. This focus is very, very different. The focus here is on the printing side. So we have special tools for doing that. The coolest one is Recast, and JS Go Shift is essentially a different API on top of Recast. So Recast is this tool that allows you to write transformation of trees, and then the magic of Recast is to take these trees, the original one and the one that you produced, and understand the parts that you've changed and be as conservative as possible in printing it back. So if you didn't touch a part, it will use the original part. So in order to do so, it needs to access more than the abstract syntax trees. Of course, it needs to add the tokens. It needs to have the tokens because you want to print it back exactly as it was if you didn't touch that part. So if you have a variable declaration that you didn't touch, you don't want it to suddenly have a semicolon, for instance, because it didn't have it before, or worse things. And JS Code Shift is a tool by Facebook, which essentially does the same thing, but at Facebook scale. So it's much faster and parallelizes works, so you can run it on a big code base. And it has a nicer API, in my opinion, because instead of having the visitor API, which is the one we saw before, in which you pass an object and you do stuff, has a slightly different API that we will see, has a combinators API, like functional combinators, like using map, filters, and these kind of things. Okay, we will see the API in a second. But the tool is based on Recast, which is magical. If you look at implementation, it's amazing. It tries also to infer if your code base uses, I don't know, single quotes or double quotes, so that trees that you generated out of thin air, they use the same quotes. So it's indistinguishable that you actually didn't write that by hand. So it's pretty cool. ESLint. Who doesn't use ESLint? Wow, really? One? No, okay, just stretching. Okay, so everyone uses ESLint. And ESLint essentially is a very similar workflow, except that it doesn't produce anything other than warnings and errors, right? When you take a tree, and you just look at it, and you decide that that's a warning, or something like that. And you can write custom plugins for this. So ESLint uses ESPre as a parser. So what about if you want to lint a super custom feature that is in stage 2? So in order to do that, we have Babel ESLint, which is an incredibly clever hack on the ESLint API, which changes the parser. I mean, ESLint allows changing the parsers, but it's not very extendable in the way that it's needed to run Babel. So this is a sort of a hack, but you can use Babel instead of ESPRE. So you can use and lint all the features that you want, which is useful in some code bases. So let's do a quick demo too of this one. So writing ESLint plugins is something that is super easy, and I actually recommend, because if you have a stock ESLint set of rules is great. I mean, you extend the Airbnb one like most people do, but then you probably want to customize it for your team. And it doesn't take long. I actually did a lightning talk, I think last year at Milano.js, in which I showed that in 7 minutes, and I managed also to publish that on NPM. So it takes 7 minutes to write something useful. And it's a plugin that we actually use at work. So what I'm going to show today is something silly, but this is essentially a plugin that all of you probably have. So if you do console.log, you want to warn. And that's it. Okay? So as you see, when I'm switching to ESLint transformations, it uses Babel ESLint by default. So a thing that you want to do is essentially to look into here, the console log. How do you do that? Well, I'm going to do it in a naive way, but you essentially want to look for this call expression. So whenever I'm calling something, like a function, you can go here and query for the call expression. We're going to use this later. And then the call expression, you can explore this here in the browser. So the call expression has a few members, has a callee, which is the thing that you're calling. Okay, so you want to access the callee. And then the callee has a few things like an object. So in this case, it's a member expression. We're going to pretend that it's always a member expression. A member expression is something dot something, like you're selecting a member from an object. So in this case, we want to see whether the object here, okay, name is console. Okay. So I'm going to put this in an if. If the name is console and node, callee, instead of object, we're looking at the property, the log, which we're calling. So we go here, we do property dot name, it's log. Okay, so now we essentially are reporting this. It's awful to type like this. Okay, so do not use console log. And that's it. Your custom plugin, which is actually useful. I mean, this is very naive in the sense that it assumes that your console log is going to be exactly like that. But I think the actual implementation in ESLint is very similar, like is probably the same or something like that. Okay, so it's super easy. But you can prevent, like a builder, for instance, we don't use for loops or any loop. We just use map and filter and reduce and these kind of combinators. Sounds crazy, but it works. We have several thousands, tens of thousands of lines of code in JavaScript that don't use any loop. So we forbid that. So you can just go here and take and do like for expression or for a for statement and prevent that. You just do context report, do not use for. When you use a for here, I don't even, can you do this? Probably. Yeah, do not use for, that's it. That's the shortest useful linting rule that I know. Okay, so you can customize that for your team, and that's actually great. And it's essentially the same API as you noticed from before. It's the same API as Babel. You just manipulate a tree, and here it is. Okay, so what about ESLint ---- fix? Okay, I didn't draw that. And actually, ESLint fix is a very different workflow than, for instance, the CODEMOD. It doesn't work on a tree transformation. You don't do a tree transformation in the sense that you don't change the data structure and then somebody prints it. You actually go and change the text, which is extremely different as an approach, which is extremely more dangerous in the sense that you can produce invalid programs. You can just do anything and just delete the whole line and the program doesn't compile anymore, parse anymore. But it's actually interesting as a trade-off, because if you want to be absolutely precise, and if some of your fixes include changing exactly a white space or a semicolon, you have to do that. Because in the abstract syntax tree where you don't have the concept of a semicolon, so you cannot just add or remove a semicolon, you need to work on the text, on the tokens. So that's why ESLint ---- fix, if you write a fix, you get a string and you need to manipulate that string. So that's the reason why, because they care about spaces. That's the whole point of the linter to some extent. PRETTIER, who uses automatic formatting of code? Okay, a decent number of people. We don't yet, but we will eventually. So Prettier is a code formatting tool. So Prettier actually exploits the fact that an AST forgets information. So it just takes your code, puts it into an AST, and just forgets about everything you may have done there and prints it back in a reasonable way, following some rules that you defined. So you want to print it just with single quotes? Do it. You just print it back. So Prettier does that. And hold on a second. Okay, so Prettier does that. And now Prettier supports a few other languages, including TypeScript. So based on what we saw today, can you guess why it took so long for Prettier to support TypeScript? Any guess? Anyone? For real? Different AST, right? Prettier, of course, works with some AST. The whole core of Prettier is this arrow. So the input is an ES3 kind of tree, and it prints it to source code. And if you give it a TypeScript AST, it doesn't work, period. So you have two choices there. You can rewrite a similar tool for TypeScript, or you can do what has been done, which is take the TypeScript tree, transform it to a tree that Prettier can understand, and then you get all the goodies from Prettier for free. So you don't need to rewrite Prettier, you just need to change the input. You manipulate the input of Prettier from TypeScript to ES3, and then you can pass it to Prettier, and does its job. So meanwhile, in the real world, so these are like toy examples, but I want to talk to you about a case that we actually had at work, in which we were faced with a decision of automating this or doing this by hand. So we had this kind of API. It doesn't need to make sense to you. I mean, it's a very custom API. But the important part is that here we define in line whether a this is like prop types in React, if you know React. But essentially what we do there is flag is a Boolean, name is a string, and label is maybe a string. So it can be there or not, okay? So we do this all the time. And this is specific to a single component. So this is a local definition of a type. So we're saying name is a string here. What we wanted to do is to take these definitions and make them unique across the application. So whenever we refer to name, name is going to be a string. So we want to have this file, like state.js file or whatever JS file that says name is a string. That's it. And whenever you use that, we change the API. So instead of doing this object in which you say name is a string, you simply say I'm connecting to name. Okay, so you have an array of the keys of the objects from before. So the interesting thing that we have to do now is to go around and change all the objects like is flag, boolean, name, string, label, t, maybe t string to just be an array of is flag, name, and label. Okay, it's a stupidly tiny change in the API, but if you have like hundreds of this, it's going to be very painful. Okay, so this is just an example, but I can imagine that you had to do some kind of manual rewrite of this at work at some point. Okay, so now we have this thing and we want to just refer to that. How can we do it? So, I mentioned before JS Code Shift, which is a tool for transforming code bases, and the output of this code base is something that you keep using. Right? So it's an intermediate step that you run once and then you just move on with the same code. So what we can do here is essentially, okay, let's suppose that we have something like this. Actually, let's do this. Okay. Okay. So we have this. Okay. So what we want to do is to use the JS Code Shift API to go find that connect, find that object, and replace it with an array of the keys of the same object. Which should be doable. So again, I'm not going to explain the API that much, mostly because I don't know most of it. So this is file source. Okay. So as I mentioned before, this is a very different API than the visitor pattern. We use combinators. So instead of doing like, I'm going to find all the kind of trees made like this, passing an object, what you do here instead is to do find. And you find what you're looking for. You're looking for disconnect. So you're finding a call expression. So you do find j call expression. Okay. I think. Sorry, I'm running. Okay, yeah, works like this. Sorry, too many APIs to remember. So once you find all the code expressions, you essentially have like this stream of code expressions, all these code expressions that the parser could find in your code. So now you want to filter the ones that have the shape that you want. So we want to look for a container. So this path here has a node, and node is this one. Okay, so we want to look whether the identifier, so the callee name is container. So now we have all the containers, all the call to containers, and we want to do something with those. So for each one of those, okay, so for each one of those, what we want to do? So we want to find that connect. So that connect is path node. Now we're looking at this. So path node is this call expression. So you want to find the arguments. Let's assume there's always going to be a second argument. So this is this object here. So now what we have in hand is this object here. So arguments, object expression. And now you want to essentially take the properties of this object. So what we want to do here is to do properties, and we want to take the property that is called connect. So if key name, we want to filter on the properties. So these are the properties of this object here, right? So we want to find the one that is connect. So prop, we do prop key name equal connect, and we see whether we find it. Okay, so now we have the connect, and if we have the connect, I want to just assume that we find it, which is obvious in this case, but you can make it is more robust. Now that we have it, we want to essentially take the connect value, which is this object here, and replace it with the keys of that object. So this may seem complicated, but it's actually very simple in the sense that you do connect. You can just take the props, you do connect, which is this object expression here. Okay. You take the value, which is an object expression again. You take all the properties. And what you can do is to map on the properties, and we want to transform every key of the property into a literal string with the name of that property. So what you do is to map the prop, and you create a literal with the prop key. Okay, now you have essentially an array of these keys, and what you can do is here is to do const, is to do connect value. We want to replace the connect value, and we do J, which is the JS Code Shift API, array expression of these props. I made a mistake here. Okay, I made a mistake, but as in kitchen TV shows, I have the complete version here. So let's pretend it doesn't happen. So I'm actually being more conservative here, so I'm looking for the connect. So as you can see here, we're essentially creating this literal. So the least intuitive part is when you create the literal, because you have this thing, but you want to transform that into an abstract syntax tree kind of node. So you want to turn the string into a literal. And then the same thing, you have an array of stuff, but you want to transform that into an expression, an array expression. So what happened here, if you look at the input and the output, is that you have all the keys here. And this saves days of work, maybe weeks of work if you have a huge code base. So to recap what we saw, why and what are ASTs? Why are they useful? Why are they so needed? And they're essentially fundamental to any useful thing you do with your code, other than reading it. In JavaScript, there's many competing standards, and well, you may just need to be aware of those. So if you want to experiment, just choose the one that makes sense in your case. And then we saw some AST-based workflows. So we saw the Babel workflow, we saw the PRETTIER workflow, we saw the CODEMOD, ESLint, and finally the execution workflow. So these workflows are all powered by the fact that you have an AST and you can manipulate that and work with that. So this is a very powerful skill set. And again, you may guess that it's not unique to JavaScript. You can do this in Scala, and I actually do this a lot in Scala. Same thing. You can produce amazing dev tools out of nothing because you know this thing. I was actually talking to David here about PostCSS, and he told me, yeah, it's AST manipulation. Yes, of course. It's the same thing all over in many different contexts that you may not even know today. I'll leave you with some resources if you want to explore on this stuff. Of course, ASTExplorer.net. And the Babel handbook is actually pretty great in explaining how the whole toolchain works. And thank you.